figure out what kind of locomotives we're going to use to haul them. And so being as we're talking about modern locomotives here, I've appropriately put up a 1936 Pennsylvania Railroad calendar of a GG1 electric locomotive whisking a fast passenger train along the river towards Washington, D.C. And you're probably wondering what in the world this has to do with modern locomotives, but it actually has to do a lot, and that's because the electrification project between New York and Washington, D.C. and the development of the GG1 electric locomotive pretty much proved the superiority of using electrically powered trains in high-speed passenger service, and that is a fact that still holds up very much so today. So let me just talk a little bit about the discoveries and the testing and development of the GG1s back in the 1930s. The railroad had just been electrified with 11,000 volts alternating current catenary between New York City and Washington, D.C. And the Pennsylvania Railroad borrowed a lot of electric locomotives from other railroads for testing and eventually developed the GG1. This locomotive was able to output a continuous horsepower of about 4,600, which was much more than any other locomotive of its time, whether steam or diesel, which was still in its infancy back then. And this allowed the railroad to haul up to 18-car trains at 90 miles an hour on the level track between the two cities. Basically, by using one locomotive to haul a long train instead of many, they were able to move trains faster and also save cost on crews and trains. But what they really discovered in testing this locomotive is that it was able to generate very high levels of short-term, or what we call non-continuous horsepower. This is something that diesel locomotives and other internal combustion engines can't do. Effectively, the electric engines are able to kind of overload themselves for short periods of time in order to almost double their horsepower. And in tests it was discovered the GG1 was able to generate about 9,300 horsepower at the wheel of short-term horsepower, which even by today's standards would be the equivalent of about 3 diesel locomotives. So even back then they were able to do that. This allowed it to accelerate up to 100 miles an hour with test trains in just over 64 seconds, and allowed it to achieve a top speed of up to 128 miles an hour, although in revenue service they were usually limited to about 100 miles an hour. So we move on to electric locomotives today, and we find that their superiority still holds. In general, for conventional railroad service, electric locomotives have a top speed of 125 miles an hour, versus diesels usually having a top speed of only about 100. Once again, the short-term horsepower of the electric engine ranges from about 7,000 to 8,400, versus the diesels about 3,000 to 4,000 horsepower. Electric locomotives also achieve a higher rate of horsepower with lower weight on the axles. For example, your typical modern electric engine that Amtrak uses today has only 206,000 pounds of weight on the axles, versus a modern diesel which has about 288,000 pounds on the axles. Electric locomotives are not only better at accelerating, but they're better at braking, because what they can do is they can reverse their electric traction motors on the wheels and actually use them as generators to brake the train, which is much more effective at very high speeds than using tread brakes or brake shoes on the train. This also means that they can feed this power back into the alternating current catenary, and other trains on the railroad can use it. In fact, in Switzerland, where trains use regenerative braking to descend long mountains, they actually have been able to recover about 20% of the electricity used. So your trains actually generate power for your own railroad. The FRA has conducted speed tests using modern diesel and electric locomotives, and the electric locomotive came out on top. This is a modern Amtrak P40 diesel locomotive here. With the 4-car train, it takes it about 2.7 minutes to accelerate up to 90 miles an hour. The modern electric engine can hit 125 miles an hour with a 4-car train in the same amount of time. So as you can imagine, that saves you a lot of running time because you can actually do your track speed instead of wasting a lot of time accelerating and braking into and out of curves and stations. Now, using electricity does have some major weaknesses, mainly that the catenary is susceptible to being blown down by strong winds or having trees getting tangled in the wires, which this is a piece of catenary right here catching on fire near Morristown, New Jersey after a tree came down in it. And because electric locomotives have a very high horsepower to weight ratio, they're very susceptible to being delayed due to slippery rail conditions, like when leaves fall down on the rails and get crushed in the fall, or when it rains or snows on the rails, and that can lead to wheel slip and delay trains. Now, the most popular method of powering passenger trains in the U.S. is the diesel locomotive. Diesel locomotives in the United States aren't the same as they are in Europe. Over in Europe, they usually are diesel hydraulic, but in the U.S., the engines are effectively electric locomotives, but with onboard diesel generators. In other words, they have traction motors on the axles that provide power to the wheels, but the electricity for those traction motors is generated by an onboard diesel prime mover, which when it turns an alternator or generator, which generates the electricity. So these engines have a major advantage in that they don't require a huge and expensive investment in catenary and a power supply system and its maintenance. This means that they're more suitable for low-density lines where you can't justify the high cost of electrification. Their major disadvantages are, as stated before, they're very heavy, they're pretty slow on the acceleration, and they have a limited top speed. Now, as we talked about in the history section, it seemed that gas turbine engines had a promise for a while, and as the European and foreign studies people said, France thought that was the way to go, and as did the US back in the 60s and 70s. But unfortunately, these engines turn out to be pretty difficult to maintain, and they're very fuel hungry. So with fuel prices rising today, we probably don't want to even consider using them. Now, here's something a little bit different, which has seen some pretty significant advances recently, and this is the dual-mode locomotive. It's an engine that's capable of running both off of internal combustion power or electric power, either from overhead catenary or a third rail. And actually right now some of these engines are used for the trains between Albany and New York City. Basically they used to change engines on those trains, which took a long time, but then they got the dual mode locomotives, so when you get near New York City they change over to electric power and you go right on through the tunnels and into Penn Station, New York. So you definitely could do that, but because these locomotives are very heavy and expensive, you're probably only going to be able to justify doing it in areas where you don't want to electrify most of your railroad, but you have to use tunnels to get into your city. Electric multiple unit cars are another option, either electric or diesel for that matter. I think diesels are becoming more popular today. Japan, as you mentioned, has experimented with these, as to the United States with the Metroliners and the Silverliners shown here. Basically, with a multiple unit train set, each car is its own locomotive with its own traction motors and onboard, or either that or getting its power from overhead catenary. And this allows for rapid acceleration, and not only that, but the components on the train hold up well in stop-and-go service, like especially commuter service, because the weight and the wear and tear is distributed over the entire train instead of being concentrated in one locomotive. So these are very effective, but once again, fairly expensive, and they require a lot of maintenance because each car is a locomotive itself and therefore has to have a 30, 90-day inspection and various other maintenance that other locomotives have. So finally, we get to our most exotic power source, which is magnets. There are two types of maglev trains, one of which uses attractive forces to levitate above and move along an iron rail. And we can also use superconducting magnets, but that's even more exotic, and I'm not sure if anyone even does that yet. The primary advantages of maglev trains is that they're very fast, going up to around 300 miles an hour, and this means that potentially they can compete in markets with air for cities that are much further apart than higher speed rail or conventional steel wheel high-speed rail. The major disadvantage is that they require all new right-of-way. You can't like switch on to running on regular railroad tracks when you get to crowded areas where it's hard to find land to build a new right-of-way. And they are very expensive to build, costing about $20 to $50 million per mile versus top dollar TGV style steel rail, high-speed rail, which cost about $10 million to $45 million. And so that's it.